maybe sometime before one. Yeah, flexibility. Cool. So hide focus. It's probably too difficult to
That's all. While we're waiting for a few other people maybe still coming in, were there any questions from the first part today? Any things that you sort of wondered about, or maybe not questions, anything interesting or surprising or unexpected? Yeah. Yeah, you can use it for anything, long-term climate studies. It's just that because radar is very fast periods of observations, like it's electromagnetic waves bouncing off something very quickly. So you can get that really fine temporal detail. So it provides that advantage over something like a rain falling into a bucket, which you can't get as much detail at very short accuracy like that. So, and also you can pick up some spatial details in moment to moment. So it's got benefits in that way. But you can also look at long-term averages as well, which is useful too. AGCD is from the actual station observations that you saw. There's the screens are and things. It's actually how much rain is being fell into a measuring instrument, and then a person comes along and reads it and writes it down. That's partly why this like Sunday, Monday, Tuesday things, like maybe some people aren't working as much on a Monday morning, maybe in South Australia back in the day, but there might be something like that. Differences and things. We talked about Sunday, Monday issue. So that's how the AGCD comes, and then they do it was called a modified Barnes interpolation, which is a spatial mapping of over these areas where there's not much, but you can't go too far. About 2 years ago, they updated the averaging method. Yeah, and now the new method, there used to be this big gap out in the western desert regions. Now that gap has disappeared because they've used a better method. And so if you look at the new monthly data AGCD, you don't get this anomalous gap in the west because they've used a different method that can go out a bit further. So that's a recent improvement. But yeah. Data set only for monthly so far. I keep asking, when's the daily going to be available? So as soon as the daily gets available, heaps of things will be redone with improved. It's 0.05 degrees, so that's about 5 kilometre that long. Yeah. All right. Any more final questions before we? Here we go. One. Great. Fantastic. All right. Well, I might pass over to Andrew Brown. Dr. Andrew Brown, thanks very much.
Yeah, thanks. Thanks, everyone. Yeah, thanks for having me. I'm keen to talk today about more about storms and thinking a bit more about what we know in terms of the climate and variability of thunderstorms, or what we know, and I guess more so like a lot of what we don't know as well, and to what extent we can say things about how thunderstorms might be changing with climate change as well into the future. Do I have to click record or anything? No, it's already. I started recording. Oh yeah. Great. All good. So, just a little bit about me. To introduce myself, so I did a Bachelor of Science and Honours Research here at Uni Melb. And then I went and did a few different research projects in climate and weather meteorology. So extreme rainfall and tropical cyclone work, and then started working on severe thunderstorms with Andrew here, and particularly looking at wind gusts from storms. And then I went from that to doing my PhD back here at the university on that problem of severe thunderstorm winds and how they might be changing in the future under climate change. And recently completed that PhD, and now I'm a research fellow here at the school, looking at coastal winds, less extreme, but more daily variations in coastal winds. And this was probably the most exciting part of my PhD. I got to go on scientific research vessel, the CSIRO's investigator ship, and do some weather balloon launches. Andrew was also involved in that project as well. Most of the time I was sitting at my desk doing coding. You get to do some, you do sometimes have the opportunity to do some exciting things in this field, like go out and launch balloons. I'm sure you've probably touched on this, so let's start just with defining what we mean by severe thunderstorms. So I guess we'll follow the Bureau of Meteorology's definition here, and thinking about any thunderstorm that produces any one of these hazards. So either large hail, damaging wind gusts, heavy rainfall, or tornadoes. And yeah, we've also been through this too, but we know that severe thunderstorms can produce a lot of hazards at the surface. And I won't go through a lot of these, but you can have quite large insurance losses from hailstorms. And some of the most costliest insurance claims events in Australia have been from hailstorms. This is a graph here of insured losses from 2017. It's quite old now, but the hazards that cause the most insured losses in Australia, and hailstorms and thunderstorms are right up there as being costly events. It can also lead to bushfire emissions and electricity network outages from things like downed trees. Then you can get these hailstones. This is a hailstone from Italy. Across is like forest scale. So yeah, you can obviously get quite strong impacts from thunderstorms. But there also can be a positive. So some studies have shown they're quite important for like the hydrological cycle and bringing rainfall to a lot of regions around the world. So this is a map showing the percentage contributions to rain at a bunch of locations across the globe from convective storms or large convective storms. So in some regions, it can be more than half the average rainfall is due to convective storms. So yeah, we mostly think about severe thunderstorms as a hazard, but they can be important for thinking about rainfall as well. So yeah, because of all this, it's obviously important to know both when and where severe thunderstorms occur. And then also they're changing throughout the historical record and into the future to help with planning. So yeah, I guess I'll refer to this as sort of long-term variability, thinking about sort of decadal changes in severe thunderstorm occurrences and intensity. So yeah, I guess maybe might have touched on this in the previous hour, but part of the problem for assessing long-term variability in thunderstorms is that thunderstorms occur on quite small spatial scales. So maybe from the kilometer scale to like tens of kilometer scales, which is often below the density of our observational network. So oftentimes we'll miss thunderstorms completely in our observations. And they're also quite hard to model with our weather and climate models because of those small scales. Yeah, if we're thinking about weather and climate models, often they'll have like grid boxes of tens of kilometers to hundreds of kilometers scale. So yeah, often thunderstorms are occurring below that scale, so we can't really model them properly in a lot of contexts when we're thinking about climate projections and change. And then, yeah, observations of a lot of times these are inhomogeneous. It's hard to say, meaning that they change throughout time. So, yeah, if we look at thunderstorm reports, this is for Europe, you can see over this 20-year period, 30-year period, there's way more events being reported in the recent period, and that's obviously not because of a massive increase in thunderstorms. It's more so to do with the reporting practices and social media and stuff, meaning that we have lots more reports of thunderstorms now than in this previous period. So we can't rely on these types of thunderstorm reports because they're changing in time for assessing variability in storms. And then we do have some other sources of observations, like the radar network, but some of the radars are quite short, like maybe 10, 20 years of data, which can start to give you a picture of long-term or climate variability in storms, but it can't obviously tell us anything about future climate change. And we also have gaps in this network through some perfectly covering Australia. So yeah, we don't really have that complete picture. The result is that, yeah, understanding changes in thunderstorms and their hazards generally less understood than other what I would call like large scale hazards like heat waves and large scale precipitation events. If you think about this is just a graph showing like a schematic of expert knowledge of in our field of changes in different events. So these sort of larger scale events are more well understood compared with things like thunderstorm winds and hail and tornadoes. And it's generally to do with the small spatial scale combined with relative lack of consistent observations. So yeah, our way around this a little bit is to generally think about thunderstorm variability by considering environmental factors, or I might call them environmental ingredients as well. And I'll talk a lot about this today. I'll explain what we mean by this. So yeah, I'm going to talk about firstly for the historical climate, explaining this idea of large-scale thunderstorm ingredients, and then looking at climatology and trends in the historical climate in these severe thunderstorm environments. Sometimes they're also called environmental proxies. And then we'll talk about them in the future climate, so future projections of thunderstorm environments. And then talk a little bit about not only thinking just about severe thunderstorms, but thinking about individual hazards like hail and winds, which is what I've done some research on. And then I'll talk a little bit at the end, if we get time, about sort of where we're heading in terms of the science of climate modeling, which is these so-called convection models, which I'll explain. So yeah, firstly, what are these environmental ingredients? So I'm not sure if this is new information or not, but generally, thinking about severe thunderstorms, we often need, or we do need these ingredients for them to occur. So we need moisture at the surface to to fuel the thunderstorms essentially. And we need some atmospheric instability. So we need warm air at the surface and cold air aloft. We also need some, what I'll call a lifting mechanism. So something to kickstart the updraft essentially. And we also need vertical wind shear for severe storms. So vertical wind shear has a couple of roles, but I guess the simple way to think about it is sort of if you have your warm, moist thunderstorm updraft going up into the atmosphere. If you have wind shear, so changes in the wind with height, then you can get that air at the top of the storm being convected, and you get the downdraft, so the downwards air and rainfall in the storm that occurs separately from the updraft. So you get this separation between the updraft and the downdraft. If we didn't have wind shear, maybe the downdraft would just fall back straight through the updraft and you would get the storm dissipating. But yeah, wind shear is another ingredient that can lead to more severe storms. So these are our key ingredients. You need moisture. So moisture is giving you energy through when the air rises and the moisture condenses, and it releases heat. So that's fueling the updraft. Instability, so that's, yeah, the warm air being relatively warm compared with the cold air aloft. So the warm air wants to keep rising. The lift for an initial kickstart and the vertical wind shear. So for our ingredients, yeah, we'll focus a lot on moisture and instability and vertical wind shear, not so much about lift, but I'll explain these in a bit more detail now. So we can measure moisture and instability in the atmosphere as well as vertical wind shear by looking at the vertical profile. So often we can do this by radio songs, like through the weather balloons that I showed before, or we can look at this in our models as well, weather. So we'll often summarize these moisture and instability measures through something called a QT log P diagram. And it's complicated, but we'll go through it. And through that, we can get this quantity called CAPE, or convective available potential energy. So this summarizes the amount of energy in the vertical that's available for a thunderstorm updraft. So this is what a SKU-T log P diagram sort of looks like. It's like a simplified version. I don't know if anyone's seen this before, but we often use it when we're thinking about severe thunderstorms.
Maybe hands up who's seen it before.
Okay, quite a few people. That's good. Well, it'll be a good refresher. I'll go through it anyway. So, yeah, our temperature, our temperatures are on the horizontal axis. They're skewed a little bit, so they go these orange lines here. So it's called like a skew T. And then in the vertical is pressure, but it's the logarithm of pressure. So it's called the log P. But you can essentially just think about it as height in the atmosphere. And then the red line is the air temperature in the environment, and the blue line is the dew point temperature, or the temperature at which the air will start to condense the water vapor out of it. So that's our moisture and our temperature of the air. Then we have this black line. So this black line is our theoretical air parcel if we were to lift air parcel up from the surface. We know that it has some moisture in the surface, but it's not yet saturated in water because it's not at its dew point temperature. So it'll rise under what we call tri-adiabatic conditions, which we have lines on this diagram, so we can draw a line parallel to those lines. So it cools as it rises under these conditions. And then when it reaches its dew point temperature, that's when the moisture in the air, our hypothetical air parcel will start to condense, and that condensation leads to warming of that air, and so it keeps rising, but at a warmer temperature than it would because of this condensation. So this is what we call the moist adiabatic temperature decrease. So it's still decreasing with height, temperature with height, but slower than under dry adiabatic conditions. So basically, because of the theory of the stuff of the thermodynamics, we know that our theoretical air parcel from the surface will rise at a temperature of this black line. So then this is where it gets, I think, interesting, because you have some parts of the profile where this black line is warmer than the environment. So under those conditions, our hypothetical air parcel needs to rise, and that would be more conducive to having like thunderstorm updraft. If we add up all this red area, the difference between our hypothetical air parcel and the environmental air, that's what gives us this CAPE, convective available potential. So it's the energy that would be available to have an air parcel rise through the atmosphere. And the more CAPE there is, the stronger the updraft would be. We also have these blue areas. So these blue areas are where our theoretical air parcel is colder than the environment. And under those conditions, our parcel would want to sink. So those areas are what we call inhibiting the convection, or convective inhibition, SIN is what we call it for short. So these are the regions of the atmosphere that are not conducive to convection. And this is where this lifting mechanism comes in, this initial kickstart that you need to sort of get your air parcel over these blue areas so that you can sort of unlock this CAPE, available potential energy higher up. So that's where this lifting comes into it when we're talking about convective inhibition. Does that make sense? Does anyone have questions about this before we go on? So I'll talk about CAPE a lot, so it's worth sort of taking the time now. Yeah, I mean, yeah, it doesn't matter if you don't understand like the exact way we get the lapse rates and stuff from the thermodynamics, but yeah, just to note that it's sort of this measure of where an air parcel that we lift will be warmer than the environmental air above it. That's sort of the main idea. And it depends on the moisture and the temperature at the surface, is how much CAPE you'll get, as well as what the environmental temperature is higher up in the atmosphere. So these ingredients like CAPE, moisture, temperature, as well as the vertical wind shear, they're driven primarily by larger scale motions in the atmosphere. Small scales can be important for this. They can modify this environment, but generally when we're talking about CAPE, we're thinking about synoptic large-scale sort of motions. This is a real example of the same diagram. So this is this case for Italy, where we had this like enormous hailstorm. This is a profile taken from near the event. So here we have our black line on the left, that is our dew point temperature. And we have a black line on the right, so that's our air temperature. And this red line represents this theoretical air parcel that we would lift from the surface. And you can see I've shaded the regions where that air parcel is warmer than the environmental temperature. And we can add up that region to give us some value of CAPE. In this case, 1200, which is a pretty high value. And we also have this region lower in the atmosphere where our air parcel is colder than the environment. So we have some amount of convective inhibition as well. I think it's somewhere here. This energy we need to overcome through a lifting mechanism. And the map shows the colors are where are the Cape values. The wind barbs, which are kind of hard to see. You can see the little flags here and the little arrows, the little barbs. Those are the wind shear. So to say here that we had high values of wind shear interacting with high values of Cape. So these are our two ingredients, two of our ingredients that come together to give these to give this particular hailstorm event. Some people talk about this popcorn analogy of like of environment of thunderstorm ingredients. So it's kind of like bringing together like your corn kernels and your heat to create popcorn, but you don't exactly know which kernel is going to pop, but it's kind of like a broad area of favorable ingredients that we might expect some regions within that broad scale region to get some severe storms. Like for example, there's also high Cape down here. I'm not sure for this event whether we got storms there or not, but it's kind of bringing together favorable ingredients for storms. And then, yeah, just to mention again, this lifting thing. So if we have some convective inhibition near the surface, we'll need some type of what we call like mechanical lifting to actually get ourselves over that, get our air particle over that initial convective inhibition. So, yeah, there's a bunch of things that can cause this initial lifting often, and especially in Melbourne, it's like cold fronts that can come through. So you'll have this cold air that can come through, and if you have warmer air ahead of it, it sort of gets lifted up because it's positively buoyant compared with the cold air, and then that can get you to your level where you can start to unlock that Cape. So that's a common sort of lifting mechanism. You can have more complicated things going on like upper level divergence, or you can have smaller scale forces of cold air like sea breezes, or if you have a storm that rains and then cold air flows out of the bottom of the storm, that can also create this situation where you have cold air that can warm air. And yeah, topography as well. So if you have air flying over a hill, that can also create this lifting mechanism. This is just a cool animation of when these things come together. So this is Hector the convector in the Tiwi Islands, just north of Darwin, in the Northern Territory. So yeah, at certain times of the year, you'll have, because we're in the tropics, we have moisture and instability like readily available. And then in the afternoon, you get heating of this of the Tiwi Islands that can so is warmer than the air over the water. You can get a sea breeze forming, and those sea breezes can converge in the middle of the island. So like this mechanism here, so the sea breezes can converge and lift this air a little bit, and then we can get this. Oh, whoops. To the end of the talk. Yeah, you can get this release of Cape and these thunderstorms that form. And because it forms so often, it's got its own name, which is cool. You can see the cold air that comes out of the storm goes flying off to the west as well and starts to form new storms on the edge of that cold outflow as well. So that's another lifting mechanism that's happening after this. So this is a cool example of when all our ingredients come together, including lift. And then, yeah, one of our colleagues is simulating this very thing. So I just thought I'd show this animation as well, because it looks very similar to what we saw in the satellite image from before. Yeah. This is from Chris Chambers, who's in the school here. It's like 100 meters or something. So for climate, we can't run our, I think about climate projections, we can't run our models at this high resolution, but yes, but Chris is running just like 6 hours, Gili Islands. He's got all sorts of animations if you want to talk to Chris. Yeah. All right. So yeah, that was sort of a there's like a description of severe thunderstorm environments. So we need our moisture and stability, our lift, and our wind shear. And now, how can we use those to think about climatology and trends in severe thunderstorms? I just wanted to show this first. So this is actual observations of lightning over the globe for like a 16-year period. I just wanted to show this first of all to say that lightning doesn't happen uniformly. As a proxy for thunderstorms, lightning doesn't happen uniformly over the globe. Like there's a lot of spatial variability, as you can see, and also seasonally. So this animation is showing different months of the year. So yeah, it's interesting to think about, and like we're interested in what drives this variations. Like why is there more lightning in some parts of the world compared with other parts, and why does it change seasonally? And we can explain a lot of this through its ingredients. So yeah, these are what we're focusing on: moisture and instability, lift, and wind shear. When we're thinking about moisture and instability, we will combine these two measures into CAPE, and this is what we're talking about with our CAPE, this positive region on our QT diagram. That gives us our moisture and instability ingredients. We don't really have the ability to model lifting mechanisms very well. So when we're looking at trends and projections, generally we will ignore lift, not in all cases, but for what I'll talk about today, we won't consider lift. And this is one major uncertainty to keep in mind when we're talking about thunderstorm environments, is that we're not going to include lifting mechanisms. But we can include vertical wind shear. So we'll think about this deep layer shear, so the difference in the wind speed and direction between the surface, and we usually say around 6 kilometers off the atmosphere. So really, when we're talking about severe thunderstorm environments now, we're just considering CAPE and vertical wind shear. So this is a paper from 2014 showing for Australia, if you grab all the observations of thunderstorms that we have and you plot them in this CAPE and vertical wind shear space, so increasing CAPE on the x-axis, increasing shear on the y-axis, we generally see that these, as we expect, fall in the high CAPE and the high shear part of this distribution. So we can use this to actually create what we call a proxy for an environmental proxy for thunderstorm occurrence. If we just take, say, a line here, and we say all the environments on this side of this line, so everything with high CAPE and high shear, we're going to say those environments are conducive to thunderstorm occurrences, and all the environments on this side of this line, we're going to say that they're probably not conducive to thunderstorm occurrences. Obviously, we have some thunderstorms that occur on this side of the line, but if we draw a line here, it's a pretty good discriminator between our thunderstorm environments and our non-thunderstorm environments. So in this paper, they draw this line which has this this equation that we're calling S, you can draw lines higher up the distribution to try and get an idea of more severe environments. But if you just take this equation and you grab some reanalysis data, so I think if this is like 40 years of weather model data or reanalysis data, you can plot the occurrences of times that occur on the upper right side of this line, basically. And you get a distribution like this. So you get a lot of occurrences of severe thunderstorm environments in the tropics and along the East Coast. And it actually matches pretty well with our lightning observations as another sort of indicator of thunderstorm occurrences. So this is just one possible, what we call a proxy or environment of thunderstorms that is actually pretty accurate, even though we aren't including any lifting mechanisms. So it's not actual thunderstorm occurrences, it's just environments conducive to thunderstorms. It actually matches pretty well with what we see from our lightning network, observational network. This is really handy. So we now have an environmental proxy that can allow us to use our weather and climate model data to estimate historical and future trends in thunderstorms. And this gets around this problem of not having long-term records of storms, long-term consistent records. But we have a lot of global model simulations that we can look at. So this figure here is from a paper that looks at trends in these types of thunderstorm proxies. So when the environment's favorable for a storm. So on the left is climatology of how often these types of events occur. So we have hotspots in a lot of regions where we know there's a lot of storms, like in the US, Midwest, and East Coast of Australia, also in Central South America, and some areas of Europe and Asia. So when we look at trends, so this is the trend per decade of the occurrences of these environments. They're actually pretty complicated. So there's regions of increases and decreases around the world, and not much to say in terms of a robust change in severe thunderstorm environments. And this is maybe not what we would expect, and this will lead me into talking about severe thunderstorm projections in future climate. Maybe another 5 or 10 minutes. Yeah. I think I won't get to everything, but I think we've covered some things I wanted to cover. That's good. So this is for the historical climate. It's kind of a messy picture, but what should we expect for future changes in a warmer world for severe thunderstorm environments? So it turns out that CAPE is very strongly related to surface moisture in the atmosphere. So this is an older study, but it looks at just the relationship in a model between CAPE and one measure of surface humidity or moisture, in this case, the wet bulb potential temperature, basically how much moisture there is. And you can see there's a very strong relationship where if we have more moisture, then we'll have higher CAPE. And if we go back to our SKU-T diagram, and if we think about for a given environment, what will happen if we increase the moisture, this is what happens. So if we have our dew point temperature in the dashed line, and we increase that from the black to the red, so increase the moisture. If we then lift our hypothetical air parcel, it'll reach its saturation point lower in the atmosphere, and it'll start it'll start following this moist adiabat at a lower height. So essentially, you're moving this the temperature of this air parcel higher up to the right. So you're increasing the amount of CAPE, so the difference between that air parcel temperature and our environmental temperature. If you increase just the surface moisture here, this explains why we have this strong relationship between CAPE and surface moisture largely. So if you look at a map of near surface moisture over the globe, this is from a reanalysis model, it matches up pretty well with the global map of CAPE with a maximum on the equator, same as for the near surface moisture. So we have this very strong relationship between CAPE and surface moisture. And then we know that as you warm the climate, the air will generally hold more moisture due to this Clausius-Clapeyron equation. Has that been touched on yet in this? Yeah, maybe in the context of rainfall. But it's basically saying we have quite strong physical theories that relate the amount of moisture in the air to how warm it is. And if you warm the atmosphere, then under this equation, you generally have around 7% more moisture per degree of warming. That means that if we assume the relative humidity remains relatively constant, we'll have higher surface moisture in a warmer climate. And because CAPE is related to surface moisture, the CAPE also increases with global warming. This is kind of not what we saw in the historical trends where it was more mixed around the world, but this has been shown a lot with global climate models, that you have increasing CAPE with increasing temperatures due to having more moisture. And it's also been shown using theory as well. A disclaimer for relative humidity, I don't think I have to go into that, but it can get a little bit more complicated than this. Generally, this is the expectation we have that CAPE should increase with global warming. And this is just an example showing this from some global climate models for so for the historical climate, the distribution of CAPE, and what the increase is in terms of standard deviation for a mid-century and end-of-century scenario. So you can see pretty much increasing CAPE around the world, except for some ocean basin regions, but this is generally pretty robust. This study also looked in changes in wind shear. So this is the distribution of this wind shear measure from the surface to 6 kilometers over the world. The changes in vertical wind shear are a bit more complex. There's increases and decreases in different regions in the middle century and end of century. But overall, if you combine them using this sort of proxy approach, if you combine the CAPE and the shear, it's generally the CAPE that dominates the signal. So if you combine the CAPE and the shear, you get something like this, where it's increasing everywhere due to that CAPE increase. So yeah, that's sort of the state of understanding of environmental changes for severe thunderstorms, that the frequency of favorable severe thunderstorm environments are projected to increase. But again, this doesn't consider changes to actual storm occurrences, because we're not considering that one ingredient that we're ignoring here, or changes in actual hazards at the surface. So these are just those lines where we drew on the CAPE shear distribution, we drew lines to say, okay, these are our favorable environments. They just consider all thunderstorms. We're not considering sort of individual hazards, like if they produced hail or an extreme wind gust or a tornado. We're just talking here about all severe thunderstorms. I think here, I'm not 100%, but I think they used an ensemble of global models, and it's probably some indication of where the models agree or disagree on the change. And I think it's probably where the models agree on the sign of change based on where like the values are higher, you have more hatching. So it's probably like more confidence. More models suggesting the same thing. Yeah, good question. So that was going to lead me into talking about hail and wind projections, but I'm running a bit low on time, so I might not talk about this as much. This is kind of what I was saying, where yeah, we looked at our environmental proxies. So we looked at the Cape and shear distribution, and we said we're going to look at all the environments that are above this line. But if we look at our individual hazards, and these colors show where they're more likely to occur, you can see that it's not always the case that they'll occur in this high Cape and high shear part of the distribution. Like for hail, for example, they might occur with high Cape, so Cape here is on the x-axis, but they might occur with relatively low shear. Same for rainfall. Or for wind, for example, we might have cases with very low Cape but very high wind shear. So although we expect changes in Cape to cause more frequent favorable thunderstorm environments, the actual change to the hazards we get might be a little more nuanced, because maybe for wind, for example, it doesn't matter if the Cape's high or low, like you can still get wind events. So there's a bit of a step in uncertainty when we're going from severe thunderstorm environments to these individual hazards and how they might change in future climate. So I was going to talk about a couple, but I think I'll skip through this. Yeah, I think I'll skip through that. And wind is what I've done my research on. So if you want to talk more about convective wind gusts, we can talk later. But so to summarize this sort of future climate change section and how it relates to thunderstorms, we have high confidence, and this is based on IPCC, the latest IPCC report. We have high confidence in severe thunderstorm environment increases due to this increasing moisture and increasing Cape. But we actually have low confidence in what they call in the report the details of the projected changes of individual hazards. So how hail and wind and tornadoes are going to change, so the actual impact part of it. And this is due to several different factors. So the relationship, as I showed before, the relationship between the environment and the hazards, and that can be sensitive to what hazard you're talking about. The fact we're not including initiation or lift in any of our proxies. And then our proxies have been developed using historical data, so how they translate to future climate is also uncertain. As well as severe thunderstorm hazards occurring in unusual environments like with low Cape that are important for wind gusts. And then just very quickly, I wanted to mention probably where climate modeling is heading now with convection permitting models. And we saw an example Chris had from Tiwi Island simulation where you can start to actually resolve the storm in our weather and climate models. So we can go from using these proxies to actually resolving the storms and looking at the impact of future climate change through that method. So yeah, I don't think I have to go into this too much actually. All I wanted to do was mention that this is a little bit where the field is sort of heading, where our traditional models might have been sort of 100-kilometer scale grid boxes, but now we can actually get down to kilometer scale or even finer. And this diagram just shows like the actual grid spacing you need to capture different phenomena in the atmosphere. So when we start to get down to these high resolution scales in our models, we can actually start to capture thunderstorms. Yeah, and I think I've said all this already. We can actually explicitly simulate this lift initiation, so that gets around that problem of that not being in our environmental proxies. The main reason why we can't do this is because it's basically expensive to do. You need more compute power to be able to run these high resolution simulations. So, and we can't like that. But before, where they ran lots of global climate models, we can't really do that if we're running like a really fine simulation because we don't have the resources to be able to do that. So it limits what we can say about our uncertainties as well through running like an ensemble of models. Yeah, so that's it. Just to sum up, so yeah, we saw that moisture, instability, and vertical wind shear are our necessary environmental ingredients that we need for severe thunderstorms. And we can use those large-scale factors to approximate the variability in severe thunderstorms using these environmental proxies. So often this is combining the CAPE and the shear. And because they use only large-scale information, they do neglect this one of our ingredients, which is our lifting mechanism. So proxies are therefore estimates of severe thunderstorms based on the environment. They don't actually tell you where or when a severe thunderstorm will occur. And yeah, we saw that these proxies indicate increasing severe thunderstorm environments in the future due to increasing moisture and CAPE, but there's low confidence in how that relates to actual hazards at the surface. Some of these issues can be resolved through higher resolution modeling that we call convection permitting modeling, but they're kind of expensive to run. So we have some capability to do this in Australia, but it's growing. And so yeah, overall, considering all this, there's high confidence in projections, climate projections of increasing frequency in severe thunderstorm environments, but low confidence in future projections of the actual storm occurrences and their associated hazards. So it's a little bit confusing. We have high confidence in one on the one, increase in CAPE, and low confidence in what that increase in CAPE actually means for thunderstorm hazards. Sorry if I went a little bit over time. Yeah.
Any questions or comments? Might kick it off with think about, and you talked about air passing with the dial. Are there any things you think are maybe imperfect about this? Just take a parcel and lift it. In reality, what would happen? And you grab a parcel there and lift it without it changing. There's a thing called entrainment. As hot air is rising up, it's got start getting that assumes it's into the microphysics. All these models, things don't include the microphysics. So it's a large scale environmental method. And then with the change in temperature, future cases then increasing a bit, but with more convection happening, that's putting more heat up higher. So actually your temperature profile in the future is a bit, so the difference in temperature from high to low actually reduces. So instead of it getting colder as quickly as in the past, it's actually getting colder a bit less. So that temperature shift in the future counteracts some of that increased moisture. So this is two key factors for Cape. Moisture from classes cut point increases Cape, but then this reduction in your temperature rate and higher lapse rate, weaker lapse rate counteracts that, but the moisture wins.
Yeah, it can get quite complex.
Yeah.
The other thing is, as the air rises, you have a lot of liquid water and hail in the updraft that can actually weigh down on the updraft. So it's not, it's buoyant because it's warmer, but you have a lot of mass, liquid water and ice mass. So yeah, it can get very complex, especially when you have all these.
Obviously, actually put my flights to Paris for the first AR7, the next meeting. I'm on the chapter that's trying to update this. So I'm thinking we might go for medium confidence on the hazards. So we'll shift. Richard, you have a question?
Yeah, so I wonder when you just say that shift right and equal increase. What does that mean that we might not have the same impact as well, which kind of gets the energy out? In future, when you have this warming scenario, does that mean you have same degrees? I'm not sure if I'm
Yeah, no, that's another like very important factor. I think some studies have shown that SIM actually increases in the future. And again, it gets complicated because then you're thinking about the boundary layer and surface heating that can be different to like higher up in the atmosphere. But SIM is definitely important.
without saying, we might have a higher pay.
Yeah.
We don't have sync. We may not have
Increase in the future, it may be stopping things happening, but once they get through that, more intense.
Mm.
So there's a potential for fewer thunderstorms, but more intense. And you see that a little bit also with tropical cyclones. So when we do tropical cyclone week, we do it as fewer of particular weaker ones, but let's say more severe ones where that's maybe the opposite. So there's this increased proportion of intense storms result, which is sort of not what you want. The damaging ones, rather than the weaker ones that can be useful for rainfall. All right. Well, yeah, Tatiana.
Yeah, so I guess you can have a severe thunderstorm is defined as any thunderstorm that produces one of those hazards. So like a large hail, flash flooding, tornado, or a damaging wind event. Severe thunderstorm occurrence doesn't necessarily guarantee you'll get all of those things happening. Like maybe some storms will produce some of those hazards, some might produce different types of hazards. So yeah, that's not necessarily uniform, and that in turn depends on the environment a bit as well. So like if you have more rotational winds in your wind profile, that could be more favorable for a tornado, for example, because you already have some rotation of the winds in the environment that can then get a storm spinning and producing a tornado. So yeah, there is a little bit of a difference between just having a severe thunderstorm that could be producing any of those hazards, and like thinking about, okay, which of these storms are going to produce a tornado or which are going to produce large hail, or does that make sense? Yeah.
So the hazard is like the wind or the rain that makes a flood, or the lightning or the fire, and then the phenomena that may cause a hazard is, so the thunderstorms are phenomena, tropical cyclones are phenomena, and they can cause hazards like winds or flooding, or so it's a distinction there. And then we'll talk more about it later, but if you have a hazard like strong winds, risk is when you have something exposed to that hazard that's vulnerable to it. And if you've got all those things combined, you've got a risk. And then if that risk eventuates, if the house blows down from strong winds, then that's an impact. So all these words actually have kind of tight definitions in things like emergency services, frameworks. They have all these things defined. So the hazard is the wind or the flood or the fire. The phenomena would be the thunderstorm, the tropical cyclone, etc.
Yeah, like it's interesting for us if a tornado happens, but if it's in the desert or something, then it doesn't matter for emergency services.
There's no risk.
There's no risk. Yeah.
There was a cool paper last year, I think, where they looked at satellite observations out in the Nullarbor Plain, halfway to Perth from here in the desert, and they found these curious things on the ground, like these little spiral shapes, and realised it was a tornado track that had ripped up the surface of the ground and left this scarring on the ground you could see in the satellite, and then you could see when in the image it happened and find the storm. But because that tornado is out in the desert where there's no things to damage, there's no real risk from that tornado, apart from to the vegetation ripped up. All right, fantastic. Thanks very much. We might take 5, another 5. Great.
Cool. No worries. Yeah, I very quickly ran out of time because I'm like